Hi guys, my name is Lucas. I am one of the tutors in the UBC Impact Club, and I will be showing you some stuff about trigonometry today. So this is one of the topics that you will have to learn for your curriculum, and I'm going to go over everything that is on the syllabus that you can see on the screen right now. I'm going to go through these one by one. Okay, let's go. First one is a unit circle. So what is the unit circle? So you guys have done plots before, probably. So a plot is just something like this, right? You have an x-axis, you have a y-axis, and then you can draw some strange graph on it, and then you call that something, right? So we're gonna use one of these plots to illustrate the unit circle. So a unit circle is the plot that has the equation x squared plus y squared equals to 1. So any value of x and y that satisfy this equation will be a point on the unit circle. So let's see, what points will that make? Well, if we plug in x equals 1 and y equals 0, we get 1 squared plus 0 squared equals 1. So that point works. It's this point. Similarly, because you can square it, you can put a -1 and that will also work. And similarly, if you set to x to 0 and either y is 1 or -1, that works. And then we can try some other points. So you may notice that the square root of 2, if you plug that in for x and y, then the square root of 2 squared plus the square root of 2 squared is just, sorry, not square root of 2, square root of 2 divided by 2. So in this case, the square root of 2 divided by 2 squared plus the square root of 2 divided by 2 squared, this is equal to, well, you guys probably have learned exponents already and know that in this case you can just take the top and bottom of the fraction and take it to the power of 2. So square root of 2 to the power of 2 is just 2. 2 to the power of 2 is 4. If you do this again, if you add these two fractions, you get 4 out of 4, and that's equal to 1, which means that this point also works. Let's just move this to the side so it doesn't take up too much space. Which means that the point square root of 2 divided by 2 for both x and y are also on this line. Square root of 2, you may recall, is about 1.4, so this is about 0.7. The point's about right here. And similarly, for any of these square root of 2's, you can turn it into a negative square root of 2, like symmetrically flip it about this axis, and it'll always work because you square it and negative goes away. So now you can just connect these points together. If you do that, you notice that you get a plot that looks somewhat like this. This is 1, -1, -1, 1. And so this right here, this is a unit circle. So this is the graph of a unit circle. We're going to be using this unit circle a lot, so let's try to make it bigger. I'm going to draw a bigger version right here. That's 1, this is -1, this is -1, that's 1. There you go. It's not a perfect circle, but it's good enough to illustrate for now. Now let's move on to the next topic, which is trigonometric ratios from the unit circle. So I am not exactly sure how much you know about trigonometric ratios yet, but there are three main ones called sine. The abbreviation is SIN, cosine, abbreviation is COS, and tangent. The abbreviation is TAN. And so each of these, they mean something. And so they are functions. So you probably know what a function is, like f of x equals x plus 3. This is f is a function if you pass in 3, right, as the argument, you get 3 plus 3, and that's equals to 6. And so functions can have an argument and can have a value. So in this case, the function is f. The 3 is the argument, and 6 is the value. So these trig things right here, these 3 are also functions. And so for example, when we write them, we always write them using abbreviation, the 3-letter version, not the full name. You say the full name, but you write the short version. So sine, this is also a function. So it has an argument, say 0, and then it has a value, say 0. So I'm going to explain how you get the value from the argument and what the arguments mean in a second, but let's just make it clear that these are functions. Okay, so here's, before I go into unit circle and stuff, I'm going to first explain how you can get what these trig ratios mean. So let's say you have a triangle. It has to be a right triangle. So like this, it's right triangle. And then you have an angle here. And this angle, let's say that is 20 degrees. So you know that this side length here is A, and this one is B, and this one is C. So you probably know by now that there's a rule that says a squared plus b squared plus c squared. That is the Pythagoras theorem. So you know that these 3 sides are related in this way. Now you could have a bigger triangle, right? This one is bigger. But if this is still 20 degrees, so now this will be, say something else like D, E, and F. So one thing you may notice is that even though D, E, and F are bigger than A, B, and C, if you take the ratio of any of these two, they're actually the same. So for example here, if you take the ratio of B divided by A, in this case, to this graph on the left here, and then if we do similarly, like we need to use the same sides, right? E over D, these two ratios are actually the same. So because even though E is bigger and D is bigger, like if you divide the two biggers kind of cancel out, and you're left with the same ratio. And so it turns out that no matter how big or small this triangle is, as long as this angle here, as long as this is 20 degrees, as long as this is 20 degrees, the ratio of this side that's opposite of the angle and the ratio divided by the bottom side. So the length of the opposite side to the angle divided by the length of this bottom side is always going to be the same number, even if you make the triangle bigger or smaller. The only condition is that the angle is 20 degrees. What does this mean? This means that we can actually encode the fact that it's a constant by a function, because the only thing that this ratio depends on is the angle. So let's say that we have an angle, let's call it theta, and if we know the angle, then we can plug into some function f, and we will get a ratio, call that v for value. Sure. And so now we need to like think about what this means. This means that there exists a function that whenever you put in an angle, it will give you back the ratio. And this is the ratio of the side that is opposite the angle, which we'll call B from now on. So this means opposite divided by the length of the bottom side, which we're going to call A. So in order for this to work, you have to draw your triangle this way. And we give this function a name. We call this the tangent. So we use the notation tan. It's a function. You give it an angle, and it'll give you a ratio. And similarly, sine is also a function. If you feed it if you feed it an angle, it will always give you back the side opposite over the longest side, which we call the hypotenuse. That's C in this case. And finally, we have another one called cosine. It's a function, it takes in an argument, an angle, and it spits out a ratio as well. This one spits out the bottom length divided by the hypotenuse length. Okay, so now we know how these work. Let's put it to the unit circle. Actually, let's do one other thing. So for any angle, there's a rule that says the tangent is equal to the sine over the cosine of that angle. And the reason why is because sine is b divided by c and cosine is a divided by c, so we can cancel out these divided by c's. That's just the rule of algebra, and we end up with b over a, which is definition of tangent. So this rule is going to come in handy later. Okay, let's go back to the unit circle now. So let's go up here and copy our very nice big unit circle. So we're going to focus on this quadrant right here, which is the one where x and y are both positive, because the other ones are harder to explain. So let's just do this one first. So suppose that you pick a point in anywhere in this quadrant, say right here. We call this point P. It's just a point on the unit circle. There's nothing special about it. It can be literally any point on the unit circle, as long as it's in this quadrant. And what we're going to do is we're going to draw a line, a straight line connecting that point to the origin. And then we're going to draw lines vertically straight down from that point to the x-axis. And then we're going to just connect these two lines together like that. Notice you just created the right triangle, and that this right triangle looks exactly the same as the one above. And so we've created an angle. Let's call that, say the degree. Let's call that 70 degrees because this looks like it's about right. So let's say that we have 70 degrees here. And what are we going to do is we're going to find out what its cosine and sine are. So what is sine of 70 degrees and what is cosine of 70 degrees? So let's make it simple. This point P is equal to an x value and a y value, right? Because every point has an x value and a y value. So let's call this xp and yp. That is the x and y value. And here's the magic. It turns out that when you have a unit circle and you draw your thing this way, you can very easily find the cosine and sine, because the sine is equal to yp and the cosine is equal to xp. So again, this works for any case. So if I draw another one here, here's another one. We draw it to this point. Let's call this point, I don't know, R. And it will have XR and YR as its x and y coordinates. And then we draw this straight down. We get another triangle. This angle here is 10 degrees. Then we can figure out that sine of 10 degrees is equal to YR, and sine of 10 degrees is, cosine of 10 degrees is equal to XR. Alrighty? Okay, excellent. So note that this only works on a unit circle. If you make your circle if you make your circle big or small, like your circle is like this size, then and you draw a triangle this way, it doesn't work. It has to be the unit circle in order for this to work. So that's what connects the unit circle and trig ratios, is that you can read off the values of the trig functions directly by reading off the values of the coordinates of points on the unit circle, like I just showed you. Okay, now we're going to take a look at the tangent because we can't forget this one too, right? Now we know that the tangent is always equal to the sine divided by the cosine because we just showed that earlier. In this case, we can plug it in. Sine is yp and cosine is xp. So that's how you can find it. So similarly, the tangent of 10 degrees would be yr over xr. So you can find all three ratios directly just by reading off points on the unit circle. Okay. So now we're going to try and reason about some. So now we're going to introduce negative values first. So let's take a look at some of these other quadrants first. So I'm going to take my trusty little unit circle. I'm going to copy it right here again. Let's take a look at this quadrant right here, this quadrant. This is called the second quadrant. It's a quadrant where the x is negative, but the y is positive. Let's say that we take a point here. And then we do the same thing, we connect it to the origin, we draw a line straight down, and then we connect this here. Now the right angle is here, and we have an angle. Now you might be tempted to draw an angle here, right? But no, the angle always has to start from this quadrant. So like the angle, I will use a different color to emphasize, the angle needs to start here. So it always rotates from here. So the angle here is actually this. You might be wondering what angle this is. Let's say it's 135 degrees, because that's a value between 90 and 180 degrees. That makes sense. So you always have to draw your angle here. So we're going to be reasoning about this angle rather than this one. All right? Okay. So we're going to be asking what the sine of 135 degrees is, and see if there's any way that we can do this. So of course we can do the same thing as before. Label this point, let's call it A, and this is equal to XA, YA. Right? So by our rules above, the sine will just be YA. No problem, that's fine, that is actually correct. Could we do the same with the cosine? What do you think? Turns out that we actually could. Notice that the value XA is negative here because it's to the left of the y-axis. So XA is less than 0. So what does this mean? It means that the cosine is less than 0, and that's fine because cosine is allowed to be negative and sine is also allowed to be negative. In fact, tangent is also allowed to be negative. Here, the tangent is equal to YA over XA, and since YA is positive and XA is negative, it's no surprise that the result in ratio of YA divided by XA is also negative. So we have two negative values and one positive value here. So this is why we should use the unit circle when thinking about ratios, because this triangle approach, like when I showed you the triangles earlier, this only works for angles from 0 to 90 degrees. So they only work for positive sine, cosine, and tangent values. But once it becomes negative, it's much easier to visualize using this unit circle rather than trying to use these triangles to explain it. Okay. In the third quadrant, what happens, call this point B is equal to XB, YB. In the third quadrant, you still have to draw your angle all the way from here. So this angle right here, let's say this is 245 degrees, because why not? Okay? Note that this would mean that this angle right here, this one right here is, how many degrees? Is 270 minus 245, that would be 25 degrees. But anyway, we're going to be reasoning about 245 degrees. So the cosine of 245 degrees is going to be XB, which is less than 0, the sine of 245 degrees is going to be yb, which is also less than 0. So here in the third quadrant, both the cosine and sine are going to be negative, but the tangent is going to be positive, because if you divide two negative values by each other, you're going to end up with a positive value because the two negatives cancel out. And then you can try the fourth quadrant, but essentially in the fourth quadrant, it'll be opposite of the third quadrant. The tangent is still going to be negative, the cosine is going to be positive, and the sine is going to be negative. See if you can figure out why yourself, so try it yourself. I will not go on and explain the fourth quadrant. Okay. Let's see if there are any patterns in these. So suppose that we have a unit circle. I'm going to stop labeling it because you know what the points are by now. You're all familiar with the unit circle. So suppose you have a unit circle and you have a point A here, and say this is 15 degrees. All right? And this is a little badly drawn, so I'm going to try and draw it better. Okay. So then we do the same thing. We draw a point down here. And then we end up like this, right? So we have a triangle. And we can figure, so A, of course, is XA, YA. So we can figure out what sine and cosine are. Sine of 15 degrees is YA, and cosine of 15 degrees is XA, and tangent of 15 degrees is equal to YA divided by XA. Now let's say that we're given another point right here, call that B. And B is not just any random point, it's actually pretty special, because it turns out that if you draw your triangle this way, that this angle is 15 degrees. Which means this big angle here, that the one we care about, this is 165 degrees, because 15 and 165 add to 180. Okay, so now because the angle here is 165 degrees, we can figure out what sine of 165 degrees is and what cosine of 165 degrees is and what tangent of 165 degrees is. Notice I didn't label B. I didn't have XB and YB. We only have XA and YA. So let's try to figure this out in terms of XA and YA. So we know that sine of 165 degrees is going to be equal to YB. But like on here, you can easily see that YB and XB are the same value. So it turns out that this is actually just equal to XB. YB and YA are the same value, I'm sorry. And so it turns out that this is just equal to YA. It's equal to YB, which is equal to YA. So in terms of just XA and YA, it's just equal to YA. Now if we look at cosine, it's going to be 165 degrees cosine is going to be XB. But see how XB is the same distance to the y-axis as the y-axis is to XA, which means that XB is just a negative of XA, if that makes any sense. So here, in terms of just XA, and if we don't use XB at all, we're going to end up with negative XA. And so if you divide the two, you'll end up with negative YA over XA. So the general rule is that, so here's the general rule that summarizes this. In the second quadrant, in the second quadrant, so this is theta is between 90 degrees and 180 degrees. The rule says that if we, so we're gonna let alpha be 180 minus theta degrees. So in this case, if our theta is 165 degrees, alpha is 15 degrees, so alpha would just be that value right here. And let's say that we know that sine of alpha is equal to some value, call that a, and cosine of alpha is equal to b, and tangent of alpha is equal to c, then the rule says that we know we can deduce that sine of theta is equal to the same thing as sine of alpha, a. Cosine of theta is equal to negative b, because we have to flip the sign. And so similarly, we have to flip the sign of the tangent as well. So the tangent of theta is equal to negative c. So see if similarly you can find rules for the third and fourth quadrant. That's the third quadrant. This is the fourth quadrant. So there are similar rules that you can apply. If you know the ratio of the trigonometric ratios of some angle in the first quadrant, you can find some angles in the third and fourth quadrant as well that you can tell immediately just by flipping signs. So I showed you how to do it with quadrant 2, so see if you can do it with quadrants 3 and 4. I am going to move on now. So what's next? The next is the trigonometric ratios of angles greater than 360 degrees and negative angles. So now we go even further. At first we covered how to find the ratios for angles between 0 and 90 degrees, right? And then we covered how to find it for degrees from 90 to 360, so quadrants 2, 3, and 4. But what if it's even more than that? So what is the cosine of 1000 degrees, for example? So what is 1000 degrees? Well, 45 degrees goes here, 90 goes here, 135 goes here, 180 goes here, so like and then 360 goes here, right? So if you do this, you go 360, but you can keep going. 361 goes up again, and you can go round and round and round and round until you reach the angle. What this means, I know this is a terrible explanation, but essentially what this means, if you see a value, then what this means is that it's trigonometric. I'm using sine as an example, but this also applies to cosine and tangent. It's always equal to the sine of the angle minus 360 degrees. And so let's apply this rule to find the cosine of 1000. The cosine of 1000, so 1000 is greater than 360, and so this would be equal to the cosine of 1000 degrees minus 360 degrees, which is the cosine of 640 degrees. And 640 degrees is still bigger than 360 degrees, so we can shave off another 360 degrees. And what this gets us is 280 degrees. And then 280 degrees, if we draw it from the origin, it will be right here. This is 280 degrees. It's in the fourth quadrant. So then what do we know about the fourth quadrant? We know that the fourth quadrant cosine is equal to the first quadrant cosine because the x value is the same. So if you draw this point here, this is our xa, ya. We know that this will always be equal, the cosine of this value is going to just be xa, and xa is going to be the same xa as this xa here, which is xb. So we can just find this one instead. What is this angle here? Well, if this here is 280 degrees, that means 90, 90, 90, 10. So this is 10, which means this bigger, which means this part is 10. And so this part is 80 degrees. And so this part right here, this is also 80 degrees. And so this means that the cosine of 280 degrees is equal to the cosine of 80 degrees. I'm using a similar logic as what I was doing here. So if you're lost, take a look and see if you can figure it out. And then, and then we don't know what this is yet, so don't worry about it, but you can give this as the answer for now. So cosine of 1000 degrees is equal to the cosine of 80 degrees. Always try to give your answer in terms of the ratio of an angle between 0 and 90 degrees. Instead of something like cosine 640 or cosine 280, that's not really a final answer. You can do better than that. But once you get to cosine 280, you can't really do much anymore, so you can just stop here and say that's your final answer. Unless we're going to talk about later how to actually find the values of these. Okay, what about a negative angle? So here's a negative angle. So this is angle above 360 degrees. And 3b is about negative angles. So here's a negative angle. You know that if you go up this way, you'll just increase the angle. So very similarly and intuitively, if you go down this way, you'll decrease the angle. So if going up here, this is 90 degrees, then going down here, this is called negative 90 degrees. So if we rotate this way, up to here, this would be something like negative 45 degrees. Notice how if you do this and you draw the unit circle, right? If you draw the unit circle like this, you notice that this point right here, XA, YA, call that. This is the same as if you drew an angle that goes this way. And this here would, of course, be 360 minus 45 degrees, which is 315 degrees. You will get the same XA and YA. So that means the cosine of negative 45 degrees is equal to the cosine of 315 degrees. And that works for the other two ratios as well. I'm just using cosine as an example. What does this mean? This means that the cosine of any negative angle, so if theta is less than 0 degrees, then what this means is that the cosine of theta is equal to the cosine of theta plus 60 degrees. And this just goes from the fact that if you add 360 to negative 45, you get 315. And so this rule here, along with that rule above, so this rule here, along with this rule, if you know these two rules, you can find the cosine and sine of any angle. So here's an example. Find the cosine of negative 1000 degrees. So it's less than 0, so we add 360. If you do that, you'll get negative 640 degrees. And it's less than 0, so we add 360. Sorry, no negative. And if you do the math here, you will notice that this number is negative 280 degrees. And it's still less than 0. So we're going to add some thing again. And if we add again, you'll notice that this is equal to the cosine of 80 degrees. So negative 1000 degrees, you're going to have to get it by rotating this way a lot. Like this way, that's negative 360, negative 720. And if you rotate almost 3 times but not quite, you stop here. This is negative 1000 degrees. And you can notice that the point here has the same coordinates as if you just did 80 degrees, so this works out. Alright, now you understand how this stuff works. Now that you understand how all of this stuff works, we're going to move on to the next topic, using trigonometric tables. Okay, this one is very good. Let's say 4, using trig tables. What is a trig table? A trig table looks like this. What does this mean? This means that you can use a table like this to find the actual value of those functions. So for example, like before, we had all this stuff here, like here is cosine of 10 degrees, and it's equal to xr, but we don't know what xr is. So what if we actually want to find out what cosine of 10 degrees is? What is this? Like the actual value of this function. Because remember, cosine is a function. And then 10 degrees here, this is the argument. And so on the other side, this is value, but we don't have a value. So we can use a table like this. So first, we need to find the function, which is up here in the row. So this here, that's function. And then this here, on the column, this is argument. Let's bring everything to the right. Argument, which in this case is just equal to the angle. And so we can locate the function on the top here, which is cosine, right here. And then we can locate the argument, which is 10 degrees. And you want to be looking into this column called degree, this one here. So we look down here, and we find 10, and 10 is right here. And then we connect these points. Cosine goes down, 10 degrees goes down. The intersection is this value. So it's this value. Hopefully you can see where this value comes from. And so we can put this in. Cosine of 10 degrees is equal to 0.9848. It's important to note that this is not an exact value, but an approximation, because it has more than 4 decimal places. In fact, it has an infinite number of decimal places. The values of trig functions are, for the most part, irrational. They are real but irrational. And so they don't stop like this. They have way more than this. So, but the table can't show infinite number of digits, so it just shows 4 digits, 4 decimal places. What this means is that like you can just treat it as a value because it's close enough, because it's accurate to 4 decimal places, but know that you have to, so intuitively, you have to know that there's a dot 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 after here. Okay, here's an exercise for you. Pause the video if you want to try it. What is, oh, I should probably leave this here. What is tangent of 4 degrees? Okay, when you're done, resume the video. I'll talk about the answer. The answer is simple. Tangent of 4 degrees. Connect it, and it will be this value, 0.0699. So it's 0.0699 dot dot dot. All right. Now we know how to find the actual values of these functions through a trig table. Let's talk about the next topic, radian measure. Okay, so we've been using degrees. the entire time. But radians is actually a better way in math to talk about angles in degrees, because in degrees we said a circle is 360 degree and a right angle is 90 degree, but these values are kind of arbitrary, right? Nobody really invented them. So it would be good if we can figure out a more like not so arbitrary way of describing angles. So to start, we're gonna think about it like this. We have a unit circle, right? Let's say that I take any point on the unit circle, say P, and connect to the origin like we always did before. What is the length of this red line? And this origin is called O. So what is the length of OP? Think about it for a moment. Okay, let's see if we can figure it out. Well, P is equal to XP and YP, right? And since it's on the unit circle, XP squared plus YP squared has to equal to 1. This is the rule of the unit circle because it's the equation that describes it. So because of that, we can try to reason about this. If we draw a line here and here, like the triangle we always have, this length right here, the bottom length, this is just equal to XP, right? Because it goes from 0 to XP. And similarly, the vertical line here, this has a length YP because it goes from 0 to the point YP. And so by the Pythagoras theorem, we know that XP, and then let's call this one R. I'm going to explain why it's called R later. But by the Pythagoras theorem, XP squared plus YP squared has to equal to R squared, right? Because that's how right triangles work. And so if you have this equation from Pythagoras, and you also have this one from the unit circle, notice that their left sides are identical, which means that their right sides have to be identical as well, which means R squared is equal to 1. And so R is equal to plus or minus square root of 1, which is just plus or minus 1, but it doesn't make sense for this length to be negative. We don't really care about negative and positive here, so let's just, by convention, we always say that this thing is positive. So we choose a positive one when there's two choices. In this case, we choose positive 1, which means R is equal to 1. And so notice that we didn't even talk about what this angle is or like what the points are. I just gave it arbitrary 1, and even though the point is completely arbitrary, we can show that R is 1. So in fact, this works for anything. The distance from the origin to any point on the unit circle is always equal to 1. The reason why it's called R is because R stands for radius, because the distance from the middle of a circle to a point on the circle is called the radius by definition. And so we're literally finding the radius right now, and we found the radius to be 1. That's why I said R equals to 1. So property of the unit circle, radius equals to 1. The word unit means 1, in fact. It comes from the Latin word unum, which means 1. And so whenever you see unit, something, a lot of times it means 1. So that also gives it away. And this 1 refers to the fact that the radius is 1. Okay. What's next? Why did we find this? Why do we find that the radius is 1? Well, let's draw the radius circle. Let's draw the unit circle again. So we know that if we take a point, that this line is always 1. Now, what is the length of this? this part of the circle right here, that what is the length of this? Well, we don't know, but just by looking at it, it's less than 1, right? Now we draw another one. What about here? So this is 1, and again we have to start our angle here. What about this length right here? All the way from here to here. What about this length? We don't know, but it looks like it's more than 1, right? So if here is less than 1, and here is more than 1 on the other one, we can conclude that there must be some angle in the middle. There must be some magical angle somewhere around here. This magical angle, let's call it mu, stands for magical, such that the arc length, which is the part of the circle, the part of the boundary of the circle, this length here, this is exactly equal to 1. Because we know that this thing is equal to 1, right? The purple line is equal to 1. And if we can find the magical angle where the arc length is also 1, that magical angle is called a radian. So mu is called radian. So everything can be expressed in terms of this mu. So let's say that what is 2 mu? Well, 2 mu would be, well, this is 1 mu from here to here. So if we make another one from here to here, it'll go like here, right? Here's another mu. So all of this together, this here is 2 mu. So 2 mu would be 2 radian. And so just by eyeballing, it's like about maybe 110 degrees. And mu is like 50 something degrees. But in fact, we can find an exact value for how many degrees mu is, and I'll show you how to do that later. I'm just eyeballing right now. So here are some questions. How many radians are there in a circle? In 360 degrees. 360 degrees is how many radians? So by the way, it's radians. We can just write it with RAD for short. Or later on, you can just drop this completely. And if you don't put a degree symbol, this is a degree symbol, right? If you don't put a degree symbol, we're going to say that it means radian. If you want to mean degree, you must put the degree symbol. Otherwise, it means radian. Okay? That's how math works. All right. So, there's a formula for the circumference, C equals circumference. That means the length of the entire circle's boundary, like from this point all the way to that point, that length. Yeah, that's a circumference. I wrote circumstance, I'm sorry. Circumference. Alright. Okay, so there's a formula and it's equal to 2 pi times the radius. What does this mean? So the radius is equal to 1, right? Because it's a unit circle, so this circumference is 2 pi. Where do we find the circumference? Well, the arc length of the entire circle is just equal to the circumference by definition. And so we know that if the ratio between the arc lengths, so here's the arc length, right? 1, and if the ratio between the radius and the arc length, so like, okay, before I continue, the ratio between the arc length and the radius, this is always just equal to the arc length itself, right? Because the radius is 1 on the unit circle. So when we talk about this ratio, it's equal to the arc length itself. So we know that when this ratio is 1, or when the arc length is 1, then it's 1 radian. And so for 2 radian, we already said that this here is 2 radians, right? 2 mu. if this is 1, then it makes sense that this is also 1, which means the arc length is 2. So the arc length is 2, the ratio is also 2. The ratio between the arc length and the radius is 2. And so if the ratio is 1 and the arc length is 1, then the number of radians is 1. If the ratio is 2 and the arc length is 2, then the number of radians is 2. So similarly, if the ratio is 3, the arc length is 3, then the number of radians is 3. So that's what relates arc lengths, ratio between arc length and radius, and the number of radians. Which means that if the arc length is the circumference, which is 2 pi, then the ratio between the arc length and the radius is also 2 pi, which means the number of radians is 2 pi. And so 360 degrees, the entire circle, is equal to 2 pi radians. Okay? Which means that 1 degree is equal to 2 pi divided by 360 degrees radians. And so is equal to pi over 180 degrees radians. I can't write. So, which means that for any degrees, say d degrees, this would just be d degrees times pi over 180 degrees radians, and these 2 degrees cancel out. We don't have to write them anymore. And so, in short, the formula is that d degrees is equal to pi over 180 times d radians. Okay, here's an exercise. How many radians is 47 degrees? Okay, once you're done, continue the video. And the answer is we can use this formula. It's going to be equal to pi over 180 times 47 radians. So we can go to a calculator. Oops, that's not a calculator. Here's a calculator. Pi divided by 180 times 47, and it gives us 0.82 something something. So the answer is 0.82 something something radians. Okay, now we're going to go back to the original question asking what the magical angle is. So we showed that this magical angle mu is where the arc length is exactly equal to the radius. And we want to find out what the magical angle is. And in radians, it's obviously just equal to 1 radian. But in degrees, how many degrees is that 1 radian? Well, we can reverse the formula, right? If we have, say, b radians, how many degrees is it equal to? Well, if we're multiplying by this thing here, we can just divide by, we're just multiplying by the reciprocal. So we can multiply by the reciprocal, which is 180 divided by pi times b degrees. So let's try this. This is the reverse formula. You should know it. 1 radian is equal to 180 divided by pi degrees, which is equal to 57.3-ish, about equal to degrees. Okay, so mu, the magical angle up here is about 57 degrees, which means 57.3 degrees, which means 2 mu up here, this I said it was 110 degrees, that approximation is bad. That would be actually about 2 times 57.3 degrees, which is approximately 104.6 degrees. So now you know what the actual, how many degrees a radian is. we're not going to be talking about, say, 3.7 radians or 44.9 radians a lot because these are bad. We're going to talk about radians in terms of pi only. We're going to talk about pi radians, 2 pi radians, negative pi radians, pi divided by 2 radians, pi divided by 6 radians, etc. But we never talk about radians without pi. Without pi, bad. Okay, don't talk about radians without pi anymore. Now that we understand it, we are going to use pi from now on. Here is why. The reason is because a full circle 360 degrees is equal to 2 pi radians, which means 180 degrees is equal to pi radians. And so these are very nice numbers to work with, and we're going to work with multiples of these. For example, if we want to find out what 45 degrees is, then, well, 45 degrees is 100 degrees over 4. So that's pi divided by 4 radians. And then what is 30 degrees? Well, 30 degrees is 160 divided by 6. That would be pi divided by 6 radians. So see all these nice degrees we can convert to radians this way. What else are we going to talk about? Simple trigonometric graphs. Okay, excellent. So next topic is about trig graphs. That'll be the last topic for this tutorial video. After this, I will start a new video to talk about the remaining topics. So to understand trig graphs, we first need to understand what are some common values for degrees and radian for sine and cosine. So what we're going to do is we're going to fill out a table. Table goes like this. Here is the number of degrees. Here's the number of radians. And then here is the number of, and then here is the cosine and sine and tangent. And so we're going to try and fill this out for some degrees. We're going to try and fill it out for the following degrees. Negative 360 degrees, negative 330 degrees, negative 315 degrees, negative 300 degrees, negative 270 degrees, and then negative 240 degrees, negative 225 degrees, negative 210 degrees, negative 180 degrees. Okay, it's gonna go pretty long, so let's make it longer. And then if we keep going, it will be negative 150 degrees, negative 135 degrees, negative 120 degrees, negative 90 degrees, negative 60 degrees, negative 45 degrees, oops, negative 30 degrees, negative 15 degrees, sorry, no, we don't need that, say 0 degrees. Okay, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. 120 degrees, 135 degrees, 150 degrees, and 180 degrees. 210 degrees, 225 degrees, 240 degrees, and 270 degrees. 300 degrees, 315 degrees, 330 degrees, and 360 degrees. 390 degrees, 405 degrees, 400 and 400 20 degrees, 450 degrees, 480 degrees, 495 degrees, 510 degrees, and 540 degrees. Almost done, don't worry, this will be not too long. 570 degrees, 585 degrees, 600 degrees, and 630 degrees, 660 degrees, 600 and 75 degrees, 690 degrees, and finally 720 degrees. So all these angles we're going to try and fill out this table. Let's start with the easy ones first. 0 degrees. How many radians is 0 degrees? Well, it's 0 radians. And we said that 360 degrees is 2 pi radians, which means 180 degrees is pi radians. Okay. What about 90 degrees? Well, that's pi over 2. 45 would be pi over 4. 30 is pi over 6. This one would be pi over 3. See if you can reason about why. So if 30 is pi over 3, pi over 6, and negative 30 degrees is negative pi over 6. And finally, if 360 degrees is 2 pi, then 720 is 4 pi. So 340 is 3 pi. So I'm not going to fill out everything, but you can see how this works, right? And where we're getting these values from. 120 degrees is 2 pi over 3, for example. And 135 degrees is 3 pi over 4. 150 degrees is 5 pi over 6. And similarly, you can go to the negative side, which means this is negative pi over 4, this is negative pi over 3, this is negative pi over 2, this is negative pi, this is negative 2 pi. So copy the table and try to fill this out. It will be very good practice, but I'm not going to fill out the remaining part of the table. We're going to start talking about the cosine and sine now. And the tangent, of course. Okay, let's take 0 degrees. So we have our trusty unit circle. And our degrees is 0. So here we have x, a, y, a. So here, because the radius is 0, the radius is 1, xa has to also be 1. And the ya, there's no lift from the x-axis to the ya is 0. This tells us that the sine, which is y, is 0, the cosine, which is xa, is 1, and the ratio between these two is the tangent, which is also 0. So we can fill this out like this. 0, 0. So this is cosine. Cosine is 1, 0, 0. Okay. Excellent. That's 1. Let's try another one. Let's try 90 degrees. Here is 90 degrees. Actually, we should probably leave the previous one alone. Okay, let's draw another one. In 90 degrees, which is pi over 2 radians, here we have, again, xa, ya. And so xa this time is 0. Ya, because it's equal to the radius, it has to be 1. That means this is the sine. Here it's always the cosine. And so the cosine is 0, the sine is 1, and again the tangent is, well, the tangent is 1 divided by 0. What is 1 divided by 0? The 1 divided by 0 is not really defined, but if you think about it, 1 divided by 0.1 is 10, 1 divided by 0.01 is 100, 1 divided by 0.00001 is 100,000. So as this number approaches 0, then the number on the right side, the ratio becomes bigger and bigger, and eventually becomes infinity. if you make the left one 0. So if you take calculus in the future, you'll understand how this works. But essentially, the answer is infinity. Because you can make the bottom closer and closer to 0, and it'll just make the ratio bigger and bigger. And so for 90 degrees, the cosine is 0, the sine is 1, and the tangent is infinity. Okay. Now what about 180 degrees? So 180 degrees, there's still no lift, so these two are 0. But we have a rule that says that the second quadrant angles are just opposite cosine of the first quadrant, and if you draw the graph, you'll see why, so this will be -1. Similarly, the 270 degrees is kind of like 90 degrees, but the sign is flipped opposite because the y value is now negative, cosine is still 0. And so the ratio of the two will now be negative infinity. Okay, maybe we shouldn't be talking about negative and positive infinity right now because it's hard to understand. It's kind of both positive and negative depending on the sign of the 0, which can come from either side. So instead of writing negative and positive infinity, I'm just going to write undefined. Undef stands for undefined. This will make it easier to understand for the time being. I don't want to deal with, it's not correct to write positive and negative infinity here, that's why. But okay. What about these angles in between? Okay, so for 360 degrees, it's just the exact same thing as 0 degrees. So 0, 1, 0, 1, 0. No, it's 1, 0, 0, sorry. Forgot the first one is cosine. 1, 0, 0. Okay. Let's try and do some of these angles in between now. So let's take 45 degrees. Let's draw a 45-degree triangle. So again, it's going to be on a unit circle, which means that the radius is 1. If the radius is 1, this length is 1. And this length, we don't know what it is, so let's just call it A. But since it's 45 degrees, it makes sense that this one is also A. Do you see why? Think about why. Pause the video and think about why. But essentially, that means these two are the same. By the Pythagoras, that means a squared plus a squared is equal to 1, which means 2a squared is equal to 1, which means a squared is equal to 1 over 2, which means a is equal to... In this case, everything is positive, so instead of plus or minus, I'm going to skip that and just write directly square root of 1 over 2, which is equal to square root of 1 over square root of 2. Square root of 1 is 1, and square root of 2 is square root of 2, so this is the answer. It's about 0.7, by the way. So I'm going to write that in to the table. 45 degrees. A is... why do we find A? Because this point here, P, is equal to AA. Because the x value of this P is equal to A and the y value is equal to A. Which means the cosine is equal to A and the sine is equal to A. And we already know that A is 1 over the square root of 2. So we can just plug that directly in. 45 degrees. 1 over square root of 2, 1 over square root of 2, and the tangent is, well, it's that divided by that, but both of them are the same value, so the ratio of them is 1. Let's try 30 degrees. In a 30-degree case, this is your triangle. Actually, I'm gonna draw it bigger because it's too hard to visualize on here. Draw a huge unit circle. Here's 30 degrees. All right? So here's our triangle. We want to find these lengths again. Well, this one's 1, right? And we know that this is a right triangle, and the angles in the triangle has to add up to 180, so that leaves this one to be 60 degrees. And you know that when a triangle has a 60 degrees, then in this case it has to be an equilateral triangle if we extend it. So here's the other half of the equilateral. This is also 30 degrees, so this entire thing here on the left, this adds up to 60 degrees. This here is of course 60 degrees by symmetry, which means that if the radius is 1, so the radius of the circle is 1, right, which is the length of this thing here, that means the length of this has to also be 1. So from here to here, that has to also be 1, because they're the same sides, because it's equilateral triangle. So if that's 1, then what is half of that? From here to up to here, that will be 1/2. And so we already have 2/2 of the triangle. This is 1. This is 1/2. So now we need to find what is this. Well, that is simple, right? Because that thing squared plus 1/2 squared is equal to 1 squared, which means that thing squared plus 1/4 is equal to 1, which means that thing squared is equal to 3/4, which means that thing is equal to the square root of 3/4, the square root of 3 over the square root of 4. Square root of 3 is just the square root of 3, the square root of 4 is 2. So we get our final answer that the missing side is equal to the square root of 3/2. And again, now if we draw the point here, this is P. Well, the P would have the x value be equal to this length, which is the square root of 3/2. And then the y value is equal to 1/2. And this is a cosine, and that's a sine, and the ratio of the two is a tangent, so we can directly use that. The cosine is square root of 3/2, the sine is 1/2, and the ratio and the tangent is the ratio of the two, so it's 1/2 divided by the square root of 3/2, divided by 2's cancel, you end up with 1 over the square root of 3. Very similarly, for 60 degrees, 1/2 is the cosine, square root of 3/2 is the sine, and if you divide the two, you just get square root of 3 as the tangent. I'm not going to explain why right now, but following similar techniques, see if you can reason about why that is the case. I am not going to complete the rest of the table, but for practice, please copy the entire table and complete every entry in it. It will be good practice for you. And you already know how to do it. I showed you how to do these. And these angles you should try to keep in mind. Instead of using the trig table like here, you should try to use these values. And you should try to learn these values because they're going to come up over and over again in math in the future, okay? So know all of these values essentially. But especially the values between 0 and 90, these ones here, these are the most important. Okay. Now we are going to talk about trig graphs. So what is a trig graph? So like when we draw the unit circle, we drew it on a plot that has the x-axis and the y-axis. And we talked about how trig functions are functions, which means we can set y is equal to the sine of x, and that will give us a graph. So for any x and y, x here is the angle in radians, and y is the value of trig function. So x here is the argument and y is the value. I use the terms function, argument, and value a lot because I think it's very important for you to remember these terms and what they mean. Okay. Now what? Well, how do we do this? Well, we look at this table above, right? And the radians is given in this column here. And the value of the sine is given in the fourth column, which is this column here, so we can read it off. If I just copy a subset of the table, this means that when x is equal to 0, y is equal to 0, and when x is equal to pi over 6, y is equal to 1/2, and etc. These should say y. So yeah, that's how we're going to do this. So when x is equal to 0, y is equal to 0, so we put a dot here. When x is equal to pi over 6, y is equal to 1/2. So pi over 6 is, pi is about 3.14 over 6. So you can kind of see what this is about. This is about 3 plus 0.14. I'm just estimating here. 3 over 6 is about 0.5. That thing over 6 is about 0.02-ish. So this entire thing is about 0. Again, this is approximations. These are not exact values. I'm too lazy to use a calculator. 0.52. So at about 0.52, let's 1, 2, 3, etc. Probably make this longer. So remember how we talked about how we should never talk about radians without talking about pi? So it's important to locate where pi is. So this axis is good, but we should also have another axis about where pi is. So here's pi. And here is pi over 2. And here is pi over 4, etc. And so pi over 6, we say is about 0.52, so that's where pi over 6 is. And similarly on the y-axis, we're going to put some values. And we're going to try and reason about what sine of x looks like. So we're going to plug in these values from before. Pi over 6 corresponds to, I'll put another one. Pi over 3 is probably useful. It's just over 1, so this is about where pi over 3 is. Okay, so when x is equal to pi over 6, y is equal to 1/2, so we are going to put a point right here. And when x is equal to pi over 4, if we look at this graph above, then y is equal to 1 over square root of 2, which we said was about 0.7. So 0.7 would be like here, right? For pi over 4, so it'll be this point right here. right here. And then for pi over 3, what do we get? We got square root of 3 over 2, which is, well, square root of 3 is about 1.77. So square root of 3 over 2 is about 1.77 over 2. And so if you just approximate, that's about 0.885. Which means it's about like 0.7, 0.8, 0.9, so it's about here. It's about here. This here is square root of 3 over 2. Actually, I'll write these in a way that's easier to read. Okay, so then we connect this line to the pi over 3 line, and we end up with this point. And then finally, we're going to look at 90 degrees, and it says it's 1. So 90 degrees is, of course, pi over 2 radians. So if we go up here, we connect that with 1. So we get this point right here. We haven't filled out the table, so we can't do this for long, but after you filling out the table, you should try and construct the sine graph this way. But since I already know the answer, I'll just show you what the rest of the point looks like. So here, what you can do is you can just connect all of these together. That's not very good connections. I'll try to do better. So you can connect this together, so we get a part of the sine graph that looks like this. I'm not going to talk about why, because you already know how to do this stuff, so if you spend some time, you'll be able to do it yourself. But essentially, after that, it goes down, which is pi, goes back to 0, and then after that, it goes to the negative side. Okay, that's way too aggressive. Goes down faster here. I'm trying to draw this more accurately. There you go. This is better. And essentially at 2 pi, which is like right here, this here is about 2 pi. It goes first down to about 3 pi over 2, so 1.5 pi. And so 1.5 pi is somewhere like here. It's like 3 pi over 2. So at this point, it goes down to -1. That would be this point right here. And then it goes back up here. And it turns out that it has a cycle, which means that after this, the rest of the thing just repeats. Because remember that if it's greater than 360 degrees or 2 pi, then the sine is just equal to that minus 360 degrees. And if it's less than 0 degrees, it's just plus. So you can see that after every 360 degrees, it just repeats itself. So after that, it goes up, and then comes back down, and then goes down, and then it comes back up just after, because this will be 4 pi, and 4 pi is equal to 4 times 3.14, well, approximately equal to. And you know that 3.1, you know that 3.14, so that's 12.56, so it's just a little bit more than 12.5. So it'll be this point right here. right here. And then it just keeps going on and on and on. And on the same left side, it just repeats itself. And at pi, it goes back up here. And then it repeats itself. So this green curve here is y equals sine of x. We're just using the values from this table above. The x is the values here, the y is the values here, and then we're plotting all these points, and then we're connecting the dots smoothly, and we get the graph of sine. So this is what the graph of y equals sine of x looks like. The graph of y equals to cosine of x will look very similar but shifted, and if you want to know why, just look at the values above and try to reason about why. But essentially, it will start here, go to 0 here, go to the bottom here, and then it starts to go back up, right about here. It's 3 pi over 2, it returns back up, and at 2 pi it reaches its maximum again, which is right here. And then it just repeats itself. At this point right here, it goes down, and I did go down slowly. Okay. Goes here. This is minimum. That minimum is a little bit too low. These functions never go below -1 and never above +1, so that's a good thing to keep in mind. And then similarly on this left side here. This is the graph of y equals to cosine of x. And then finally for tangent, it's just a ratio of the two, and the tangent one will look a little bit harder because it has all these infinities. But essentially, if you follow the values above, and if you can also use the trig table, you can also use this to help you. Remember that now we don't look at the degree column anymore, we look at the radian column. So this is the x values, and for tangent, this would be the y values. So we can map this to that. That's how we can plot these. Okay? All right. For tangent, over here is always the green one divided by the red one. So here will be 0. I'll use blue for this. And here, when the red one is 0, that's when it goes to infinity. At pi over 4, which is where these meet, this is equal to 1. So right here it goes to 1. Let me see how to explain this. So it follows a curve that looks somewhat like this. And then after that, it goes up very, very quickly. Maybe this isn't the best way to put it, but okay, maybe that's not the best plot, but you kind of get the idea, right? After that, it keeps going up very, very quickly. This is exactly 1, and it goes up to infinity. The asymptote, a vertical asymptote, is at pi over 2, right here. So maybe I didn't approach this very well. Let's try to approach it better. I still need to get through that point, but without touching anything else, preferably. How do I draw this well? It's hard to draw on here. Oops. Okay, there you go. I think what I can try to do is do a lighter approach here. Okay. And then here we can show that it goes up towards the asymptote. And yeah. Okay. Good enough, I guess. And on the other side, it is symmetric. And so it will go down towards the asymptote at pi over negative pi over 2, which is negative 1.57-ish. So at this point, that's when it needs to go to the... So this is about right. This is negative 0.7 something. That's negative pi over 4. And that's equal to negative 1. And after that, it will just keep going down. And the new... Okay, I should use purple to be consistent. The new asymptote is right here now. It will go and approach that, but it will never reach it. So yeah, that's the tangent graph. I should probably make this entire thing a little bit spacier, so it'll be easier to illustrate. That it actually does approach very, very closely at the edges. Okay, there you go. This looks better, doesn't it? So the blue curve here, this is the tangent of x. This is y equals to the tangent of x. So that's a blue curve. This one is also cyclical, but like the other ones where it repeats itself every 2 pi, this one repeats itself every pi. Because here the range is from negative pi over 2 to pi over 2. That's where the two asymptotes are. The distance between these 2 points is only pi, not 2 pi. So it will repeat itself. I'm not going to draw in the repeats for you because you can just copy this entire thing and just start over from here and then go up and blah, blah again right after that. And same thing over here. You can just copy this top part and start going down. And so everything else is the same. So I'm not going to draw out everything. Okay? But you understand how to do this stuff now. Okay, so here are the three. The green one is the sine. The red one is the cosine. The blue one is the tangent. These are the three basic trig graphs. So if you know the shape and what they look like and the fact that they repeat themselves, which is called a periodicity. Graphs that repeat themselves are periodic graphs. As long as you know these things, you should be good to go for now. If you need more help on any of this stuff, ask your teacher at school for help, ask your fellow students who understand the concept. But as I'm going to end this video right here. Hope you learned something, and we're going to continue on with these next concepts right afterwards. Thank you, everyone.